Welcome to the video for lesson 13-4. Just a quick comment on one of the problems from homework 13-3. First of all, notice what an outstanding job I did of making it clear exactly where all of these calculations came from and what they were for, what they each represented. Look how I labeled each of these surfaces with different numbers. Isn't that clear? Who could not understand what I was doing here, right? So I've identified all of the surfaces by some description, bottom, or by some reference number, and then I've shown the calculations leading to those. This is the kind of work that you need to turn in to me in order to get full credit for a problem like this. And the one other little thing, somebody had emailed me asking me about calculating the area of this triangle, area 3A, and asking, how did I get 20 for the height of this triangle? Well, my answer to that is, notice here's a right angle in this triangle TBK, right up here. So if you spin this triangle around and turn it like this, right, TK is given to be 20, TB is given to be 20, so those 20s are here, and here's the right angle. So one of those 20s is the base, and one of those 20s is the height of this triangle. I was not making any attempt to find the height of this triangle from T down to segment BK. And I was not using segment BK as the base of this triangle. Okay, segment BK's length is clearly not going to be 20. If these legs are 20 each, clearly that's an isosceles right triangle, and the hypotenuse would be 20 times the square root of 2. No, I spun the triangle around in my head. Here it is on paper, and used a base of 20 and a height of 20. That's how I got the area of that triangle. Okay, let's move on to lesson 13-4. So I'm going to show you the blank copy of this before I show you the completed notes. Again, we want to find the volume and the total surface area of this object. This is called a cylinder. You're no stranger to that term. A cylinder has two circles congruent to each other and parallel to each other as bases. And so that seems to fit the definition of what a prism is, actually. A prism has two congruent and parallel surfaces, right? And then edges connecting those congruent and parallel surfaces. The only difference between a prism and a cylinder is that in a prism, the bases are polygons, and in a cylinder, the bases are circles. But they are essentially the same kind of object when it comes to finding the volume. And so we can use the same formula for finding the volume of a prism, the volume of a cylinder, as we can the volume of a prism. It would just be the base area times the height. Surface area, as usual, is a little more involved, in some ways a little more complicated. There are how many surfaces in the cylinder? How many distinct surfaces? Here's one circle up top. Here's another circle up the bottom. And then there's this one surface around the outside, what we would call the lateral surface of the cylinder. Three distinct surfaces. We're going to calculate all three and add them up. We'll talk about how to do that in a minute. And then for this problem, which is another new object for us, a cone, although a cone is very, very much like a pyramid. And so finding its volume is going to be just like finding a pyramid's volume. The volume formula for a pyramid is 1/3 times base area times height. It's just that in this case, the base happens to be a circle. So 1/3 times pi r squared, which would be the base area, times this height right here, which is not given to us in this problem. We'll talk about finding that length. Here's a formula you may have noticed while I was talking. This formula is for, what do you suppose LA stands for? Clearly not volume. It stands for lateral area, right? So the lateral area, the area around the cone, okay? Not the base part, but just the area around the cone, Here's a formula for it. 1/2 times the circumference of the base, and then times L, which stands for the lateral height of the cone, as opposed to the height of the cone, just plain old height, which is what we need for the volume. Okay? So let's look at the actual calculations for these objects here. For the volume, again, here's your formula for the volume of a cylinder. Exact same formula as for the volume of a prism. Base area times height. But the base area in this case is pi r squared. The radius is 3, so pi 3 squared, and then times 10. The height being the distance between the bases. Okay? Look, if we lay this cylinder down on its side, like this, okay, this is still the base area. And this distance here from one base to the other base is still technically the height of the cylinder. Even though it's not going vertically, it's what we would call the height. Okay? So volume formula, volume calculation, pretty straightforward. 90 pi is your answer there. For the surface area, we talked about 3 distinct surfaces. This circle, pi r squared, which is 9 pi. This circle area, another pi r squared, which is another 9 pi. And then that lateral surface. How do we calculate that lateral surface? I'm not going to give you a formula for the lateral surface. What I expect you to understand is that the lateral surface of a cylinder can be thought of as a rectangle. Now, you've all seen this a million times in your life. You've seen a paper towel come off of a cylindrical roll of paper towels and turn out to be a flat rectangle. Or a label come off of a soup can or a spaghetti sauce jar or something, and it turns into a perfect rectangle. Or a sheet of toilet paper coming off a roll becomes a rectangle, right? So if you imagine one paper towel wrapping perfectly around the side of this cylinder, let's say, and you unwrap that one paper towel, what would be the dimensions of that paper towel? This is actually intended to be a picture of that paper towel unrolled, and then what are the dimensions? Well, clearly the height of that paper towel, when you unroll it, is going to be the height of the original cylinder. That's easy. But what about the width of that paper towel? Well, what I've written down here is C equals 6 pi. Now, what does the C stand for, and where did the 6 pi come from? Well, you know what C stands for. It stands for circumference, the circumference of the original cylinder. That is the width of this paper towel. Here, have a look. Here's the paper towel when it's wrapped around the cylinder, right? And when you unwrap it, the width of that paper towel is what used to be wrapped around the circumference of the can, right? So to calculate the width of the rectangle, we must find the circumference of that cylinder. And circumference, of course, is equal to pi times the diameter. If the radius is 3, the diameter is 6, so the circumference is 6 pi, or the width of that rectangle is 6 pi. Now we got to calculate the area of that rectangle by multiplying the base, 6 pi, times the height, 60 pi, for the area of the lateral surface of that cylinder. Add that to the areas of the top and bottom bases, and you've got your total surface area. Okay? For the cone, then, as I said, volume formula identical to that of a pyramid, 1/3 times base area times height. The only difference, again, the base area is not a square, it's a circle. And the base area, or the area of a circle, would be pi r squared. All right. The height, we had to find this height by drawing it in, making a right angle with that radius, using the Pythagorean theorem here, a squared plus 5 squared equals 13 squared. There's that equation. Solving for a turns out to be a nice whole number, 12. Plug that in here. 12 times 1/3 times 25. all comes out to be 100. Final answer, 100 pi. Okay, pretty straightforward. And the total surface area, not that big of a deal here either. Again, I'm going to give you every formula you need on any quiz or test you get from me. Here's a formula for the lateral area of a cylinder. It's the only lateral area formula you're going to get. There are no others to be given. Okay. So the base area here, we just have these two surfaces of the cone. The base area, which is pi r squared, or 25 pi, and then the lateral area, which is 1/2 times the circumference, which again, circumference of a circle is pi times the diameter. The radius is 5, the diameter is 10. So here's the circumference, 10 pi. And then times the lateral height, which is that height, slanted height down the edge of the cone like that, 13. Add the 65 pi to the 25 pi, got your 90 pi. Okay? That's it for the notes. Let's take a look at the homework problems. I want to give you a couple of tips here before you dive into them. These are all very, very straightforward problems on the front page. Just calculate the volume, calculate the total surface area of this can. Same thing with number 2. Calculate the volume and the total surface area. Calculate the volume and the total surface area. Calculate the volume and the total surface area. But in numbers 2, 3, and 4, I've asked you to try to answer a couple of other questions. Because what I've done here is, in this problem, I've taken this can and I have doubled the height. I went from a height of 5 to a height of 10. I kept the radius the same. And all I want you to do when you calculate this can's volume and total surface area is to see if this volume is twice as much as the volume of the original can. See if this total surface area is twice as much as the original can. Maybe one of them is, maybe both of them are, maybe neither. Okay? Then, in this problem, again, I've taken the original can, but I've doubled the radius this time from 4 to 8, and I left the height alone. It stayed 5. And after you calculate the volume and total surface area, again, I want you to compare this volume to the volume from number 1. Did the volume of this can get doubled when we doubled the radius? Did the surface area of this can get doubled from the original when we doubled the radius? Again, maybe one of them did and not the other, or maybe both, or maybe neither one of them got doubled. And then finally, here's a can whose radius is twice as much as the original and whose height is twice as much as the original. Calculate its volume and total surface area, and then I'm asking you, not is it twice as much, but just how does it compare to the original volume? And again, maybe it's twice as much, or maybe not. Maybe it's something else. Maybe it's be hard to make a comparison. Maybe your answer is just, well, it's bigger. It's hard to say how much bigger, but it's bigger. Same with the surface area. Maybe it's twice as much as the original, or maybe it's some other multiple of the original, or maybe it's really hard to say and all you can say is, well, it's bigger. Okay? The answers to all of these questions really is kind of a foreshadowing of what we're going to see in lesson 13-7, which will be the third video in the series of videos and lessons for this week. All right. These are questions that, well, that's it. I won't say any more than that. Okay. I think numbers 5 and 6 are pretty straightforward. Here in number 5, excuse me, notice I'm just asking for the outer surface area of the cone. This is a cone. There is no top to it, okay? You got to be able to pour water inside of it. So you would not include the area of this circle when finding the surface area of this cone. And I really just want you to find the surface area on the outside, not on the inside of the cone. Don't count that. Let me see if I had laying around here. Oh, yeah. Here, I want you to see that if you took a sector of a circle, and it can be really any size sector. It could be 45 degrees. It could be 130 degrees. It could be 250 degrees. And if you wrap that sector around until those straight edges meet each other, look what you've got. You've got a cone, right? So for this cone, I'm asking you just to find the outer surface area. Don't find the surface area on the inside also, all right? Just the outer. I mean, the inside surface area would be exactly the same. Right? If I asked you to calculate it, it wouldn't really be any extra work, but I really just want you to find the outside surface area. Okay? Let's see. Here, okay, I want to say a couple words about this. This is a solid cylinder, but imagine it's a wooden block, a solid wooden block, a solid wooden disc, or a cylinder, I suppose I should say. And then somebody has drilled a cone-shaped hole from the top of this wooden cylinder down to a point down there. All right, and I wrote sort of like a dog food bowl, except those bowls don't come down to a point. They're sometimes flat at the bottom or a little more rounded. I want you to find the volume of wood remaining. You're going to have to subtract the volume of the cone from the volume of the cylinder. That should be pretty straightforward. But I also want you to find the total surface area of the bowl. Okay, now let's talk about that for a minute. What are the surfaces? Where are they? And how would you calculate them? Well, let's start with the bottom surface, the circular bottom of the bowl. That should be pretty straightforward. That's just a circle, right? Now you've got the outer or lateral outside surface of the cylinder. And we just talked about how to calculate that. Imagine that there's a paper towel running around the outside of that bowl, and you just unwrap it, and it becomes a really, really wide paper towel because it's going all the way around this can. It's only going to be 5 units high, but it's going to be very, very wide. And the width of that rectangle will be the circumference of the can. So there's your second surface. And then where's your third surface? There is a third one here. Where is it? And what does it look like? Well, it's the inside of the bowl. You can touch the inside of that bowl. And it has a cone shape. So this time, it's kind of like, here's the inside surface of the cone. And you can touch that surface. And I do want you to count that surface as part of the surface area of this dog food bowl, or whatever we want to call it. All right, so 3 surfaces. A circle, a very plain circle, and then the outside lateral surface of the cylinder, which becomes a rectangle, and then finally the inside cone-shaped surface. And you want that lateral area formula that was on the front page of the notes to do that. Okay. Couple comments about these problems too here. Let's start with number 8. This is a cake with a 90-degree slice cut out. Volume, find the volume as if it was complete, as if nothing had been eaten or cut away, and then just multiply that answer by what fraction? Not 1/4. You don't want to multiply by 1/4. That's the part that's missing. What fraction of the cake is still here? Not 1/4, but 3/4, right? So find the volume of the whole cylinder and then multiply by 3/4. You're done. Okay? Now, surface area, far more involved. We've got 2 rectangles staring us right in the face there. Okay? You can touch those. You got to calculate those rectangle areas, add them into the total. And then you've got a top circle, a bottom circle, and the outside lateral surface of the cylinder. But that's not a whole circle, is it? Neither the top nor the bottom is a whole circle. And that's not the entire outside lateral surface of the can either. But each of those 3 surfaces is the same fraction of a whole. What is that fraction? Well, once again, it's 3/4, right? I mean, 1/4 of this cake has been cut out. 1/4 of that top circle has been cut out, but 3/4 remains. So find the area of that circle, then multiply by 3/4. And of course, you've got the exact same area underneath. And then find the lateral area of that can as if it were complete. And then just multiply that answer by 3/4. Right? So there are top base, bottom base, outside lateral area, all three of those areas. Calculate them as if nothing had been cut away. Multiply each one of them by 3/4. Then throw in the two rectangles. Okay. Now all of the circular type shapes, those are all going to have areas in terms of pi. These rectangles will not. So the total surface area, if you give an exact answer, will be something pi plus some other value that does not have a pi in it. And those terms cannot be combined. They're not like terms if one of them has a pi in it and one of them doesn't. Okay? So if you want to leave the answer exact, which I did in my answer key, leave those terms separated with a plus in between them. Okay? Now let's go to this object up here. It's described as a solid wooden spool with a hole drilled through it. I want you to find the volume and total surface area. Again, volume, much more straightforward and easy to do than the surface area. Find the volume of that spool before the hole was drilled. Very straightforward. Volume of a cylinder. Then find the volume of that cylindrical hole and subtract the volume of the hole that's been drilled from the volume of the whole thing. That should be pretty easy. Now, total surface area, different story. We have a top surface and a bottom surface. What do each of those surfaces look like? What are they? Here. Each one of them is a circle with a circular hole. Here's the top surface right here. We got a name for this. Do you remember? It's come up multiple times now. It's called an annulus. You don't have to know that word, right? But you got to find the area of that circle, subtract the area of that circle. Okay? And then you get the same result for the bottom, of course, so you don't need to repeat that calculation. So there's the top, there's the bottom. There's the outside surface, the outside lateral surface, which once again unwraps to a rectangle. Then there's also that in the surface on the inside. Look, that cylindrical hole, when you drill it, actually creates, when you drill that hole, you take away surface area, and at the same time, you add surface area. Can you see that? Does that make sense? Here, let me show you with this object. When you drill the hole, you are removing a little circular area, a flat circular area from the top of this wooden spool and from the bottom of that wooden spool, right? You're cutting out those circles, but you are creating surface on the inside there that you can touch. Look, I'm putting this pencil inside that hole, and I can draw on the inside of this wooden spool now, or on the inside of this paper. There's surface that didn't used to be there. There's surface area that didn't used to be there until we drilled the hole. But it's there now, and you have to count it. So now you might be wondering, well, how do I calculate the inside surface of that cylindrical hole? Well, look. Look at this piece of paper. It has two sides to it, right? It's got an outside and an inside. When you unwrap this thing into a rectangle, you can see that the outside and the inside surface are exactly the same. It's the same size rectangle, right? So calculating the surface area of that cylinder inside, the inside surface, the surface that's in there, would be exactly the same as calculating the surface area that's around the outside, right? Now, I don't mean around the outside of this whole spool. The spool's got a large radius of 8, and you'll calculate the outer surface area using that dimension. But the inside cylinder, whose surface area you also have to calculate as if it were a rectangle, that's got a much smaller radius. Okay? My calculations should be very clear, exactly what I'm doing every step of the way. If you have any questions, don't hesitate to email me. I usually see those questions very quickly, and I'm able to respond very quickly. And every time I have, the students who have emailed me with those questions have told me, and I want to believe that they're telling me the truth. They've said that my answers have been very, very helpful. I also am trying to make some adjustments to how I create these videos to make them a little more clear. I've tried to bring the camera closer to the paper because somebody commented on that. I've tried to adjust the lighting a little bit. I don't know if that's making much of a difference. But here's what I want to say. When you're watching these videos, there's no reason that you can't have a copy of the notes completed in front of you while you're watching the video. Perhaps you could have them on another screen, or you could have them printed. But while I'm talking, if it's difficult for you to see something in the video, if I'm pointing to something and you're looking at it on the video going, what is that? I can't read that, what he's pointing to. Well, then hopefully you'd be able to read it more clearly on your own printed copy of the notes. I'm sure you can see what I'm pointing to, and you could look at your own copy of the notes, or maybe on the PDF of the notes on the computer that you can zoom in more on. Okay? So keep those comments coming. They're helpful to me to try to be more helpful to you. Good luck with this assignment.